So this talk is everything you always wanted to know about optical but were afraid to ask, which I've given many times, but I try to update it a little bit every time with new technology, and people keep asking for it, and it keeps being incredibly popular. So here we go one more time. So what's the purpose of this talk? Why am I talking at a routing and packet conference about optical? Well, largely everything that we do on the internet and things that even are not internet really revolve around fiber. But most router folks don't actually get a lot of exposure to it, and certainly not at the real in-depth levels of optical engineering. So there's a lot of confusion, right? There's a lot of misconceptions. People don't understand exactly how something works, or they get a little voodoo with it. Oh, it says 40 kilometer, it can't go 41. So the purpose of this talk is not to make you an optical engineer. So if you actually live in the optical world, the whole thing is nothing but math. There's lots and lots of math, all of which I'm going to skip over here. It's really just to walk through the topics and make sure that everyone's familiar with them, and then kind of answer some of the most common questions and some of the most common little tips and tricks that you can use to work with systems effectively. So even if you aren't the one designing the optical network yourself, even if you're just working with it at a packet level, it's still kind of helpful to have that information. So let's start with the basics of fiber optic transmission. So what is fiber? Why do we use it? Well, really, fiber is just a waveguide for light. So you put light in one end, and it's going to come out the other end. So it's most commonly going to be made of glass, silica of some form. It can also be plastic, but primarily you're talking about some form of glass. And the reason for that, well, one, we can do, it's super low cost, right? It's incredibly cheap and easy. You can do thousands of strands in a 1-inch cable at this point. It's really very light compared to copper especially. It's very flexible. And it's very high density. It's pretty easy to carry. Almost never do you find yourself in a situation where you've hit your capacity limit on fiber and you want to be able to do more. There is so much capacity on a particular pair of fibers that, for the most part, almost always the correct answer is I should just get another pair of fiber if you get anywhere near filling the thing up. So it's pretty easy commodity, dirt cheap stuff to do 76.8 terabits on fiber that was originally put in the ground to do 100 megabits. 30 years later, it's still fully functional. And in fact, it's actually come full circle to being preferred. The old style fiber coming back to being preferred. So it's really easy to carry a large number of signals over the same strand without interference. So we'll talk more about that later. But you can carry this signal thousands of kilometers without having, you amplify it along the way, but you don't have to do a full OEO regeneration. And the technology continues to radically improve. So it's pretty much follows Moore's law that every couple of years you're going to get this near doubling in capacity in some form or another that you're able to get out of optical technology, and that continues to progress. So here's an example of kind of a modern high-density fiber. So this is what it looks like when you actually chop one of these high-count fibers up, and you see they're all broken up into little individual ribbons and little bundles. But you're talking over 3,000 strands of fiber in a 1.2 inch, on a 1 1/4 inch cable. I'm sure there's doing more, but those are easy pictures to find off the internet. So I'll talk about the physics behind it. So remember, light propagating through a vacuum is theoretically the fastest thing that anything can travel in the universe. So that's c, right? So that's about 300,000 kilometers per second. So when light passes through a material that isn't a perfect vacuum, it propagates much slower. So actually, light always propagates at the same speed, but what happens is it goes and it hits an atom that's in its way, makes an electron jump up to a high energy state, electron decays back down, it re-emits the photon, and we see that as delay. So we call it a different rate of propagation, but what's actually happening is you're interacting with these molecules and you're re-emitting a new photon. So the speed of light for anything that is a non-vacuum, we say is the material's refractive index. So for example, water has a refractive index of 1.33, so it's 1.33 times slower than the speed of light in a vacuum. And when light tries to pass from one medium to another with a different index of refraction, you get a reflection. So if you've ever swam at the bottom of a swimming pool and you look up and you see the light being reflected back down to you instead of up, that's what you're seeing. So here's how that works inside a fiber. You have a system called total internal reflection. So the cables are composed of two layers, and this picture is not exactly to scale because the core is actually very, very small, and the cladding is much larger. But you have a core, so that's the piece that the light actually propagates through, and then you have a different piece of glass around the outside that is the cladding, and that has a higher index of refraction, so that as long as the light comes in at the correct angle, it's going to continue to bounce around inside of that and continue to propagate down the fiber and come out the other end. So here's a gratuitous example from Wikipedia using a piece of plastic and a laser pointer, and you can see exactly what's happening there. So most of the systems that we work with in fiber optics are duplex. So you have one pair of fiber for each point-to-point link. So one strand is used to go transmit one direction, and it's received on the other side, and the other strand is used to go the other direction. But the fiber itself is perfectly capable of carrying many signals and can work over a single strand just fine. It just might require more expensive components to do so. So while we talk about fiber pairs in kind of the default case, in a lot of cases, there's a lot of simplex operation. In fact, it can be even cheaper than a duplex system. But really what we use is depending on the economics. So for example, when fiber is really cheap, so I'll give you an example, Ashburn, Virginia, right? Where there's tons and tons of data centers and they're all interconnected. People will come in and install thousands of strands of fiber cables so that it's so cheap that it's cheaper to just throw commodity client optics at it and just use another fiber, just use another fiber, just use another fiber, than it is to ever consider doing any kind of an actual transmission system. But if you have constrained fiber, if you have long haul fiber, if you have something you need to amplify, or if you're just out of riser capacity or something like that, then you get into the more advanced techniques, and you're trading. If you can't get new cheap fiber, you trade some of the cost for designing a system to work with what you do have. So the most basic distinction in fiber is multimode versus single mode. So what's happening here, multimode is a much wider core. So the whole purpose of it is that you have to use these cheaper, less precisely focused light sources. It's called multimode because you have multiple modes of light. So the modes of light are dependent on the exact frequencies that you're propagating. But you're able to effectively have almost a reflection inside of itself that interferes with itself. So you get limited by modal dispersion. So typically you're somewhere in the tens to hundreds of meters. You're almost never in the kilometers or the long ranges. But it lets you use cheaper optics. And ironically, multimode fiber is actually more expensive to manufacture, but the optics end up being a lot cheaper. So that's why they get used. So the types of multimode that are out there, OM1 and OM2 are also called FIDI grade. So these were the original multimodes that came out with kind of 100 meg FIDI. So OM1 is probably the most common if you look at an orange cable. It's got a 62.5 micron core. OM2 is a 50 micron core, so it actually lets you go slightly further. But really, these are all things that were designed around 100 meg, 1310, 850, and they really start to break down at 10 gigs. It starts to be very, very sketchy if you can even get dozens of meters out of them. So the newer fibers that are out there, OM3 and OM4. So OM3 is one that typically has an aqua jacket, so this is light blue. OM4, there's a little debate on which color it is. So there's a lot of folks that use this like bright pink. There's a lot of folks that also still use aqua and just pull that into OM4. I think there's an OM5 now that's like a hideous light green. So there's some weird colors out there, but these are all modern ones that are designed really around modern high capacity. And in a lot of cases, you'll see them paired with multi-strand optics. So you'll have a 100 gig link that's designed to go maybe 50 or 100 meters that might be using 4 pairs of fibers with an MPO connector instead of just a single pair of fiber. Single mode, on the other hand, is what you pretty much see for anything that's high bandwidth or long distance. So it's going to have a much smaller core, somewhere between 8 to 10 microns. I think the SMF28 standard is like 9.2, but it actually depends a little bit based on what exact frequencies you want to carry across it. So there's no inherent distance limitations coming from modal dispersion. So a pretty standard metric is 80 kilometers is what you kind of go between where you launch on one end and where you need to do something, either receive the signal or amplify it at the other end. And that's a rough approximation. It can be 100, it can be longer. It really depends on the class of fiber, how clean it is, how clean the splices are. You can have buildings where you go through 50 splices before you leave, like 60 Hudson, for example, and you have other things where you have a straight shot with no splices with modern fiber where you're going to have very low loss. But there's also a lot of different kinds of single mode. There's way more than you see with multimode. So SMF actually has its own OS1 and OS2, but really they're talking about whether it's tight buffered or loose buffered. It's kind of how it's packaged. Really what you start talking about in single mode is all the different ITU types that are out there. So it comes in low water peak, dispersion shifted, non-zero dispersion shifted, bend insensitive. There's submarine cable systems that are designed. There's all these different kinds of standards that are out there. So here's kind of an example showing you what this looks like. So you see in single mode, you've got a very, very small core, so you really don't get these kind of interfering reflections. You don't look at these multiple modes of light inside. And if you look at the diagram here, you see how small the core of a single mode is compared to the cladding. And I think I meant to put a slide in here talking about multi-core, and I don't think I got around to it, but that's one of the things that people are coming up with now to increase the density of fiber, is you can actually put multiple cores inside of this. You can get 8, 10, 12, 16 of these cores inside of a single cladding for very high density applications. A lot of folks use this whenever you read a press release about just broke the record for capacity across a single fiber. They're like, oh, well, we used 8 cores to do it. Well, you didn't actually break the record for capacity across a fiber. You broke the record for capacity across 8 fibers. But they use it because you can say, oh, it's multi-core, and it sounds like something you would do with a processor, and people just kind of gloss over it and go, oh, they broke a record. But this is a direction that you're starting to see, is being able to put multiple cores inside of the fiber. There are a ton of different fiber connectors out there. So here's a bunch of random pictures that for reference, but there's a lot of new ones that I need to put on here. There's some new high density ones where you can get a pair in what used to be a simplex LC size. You can get even more dense than that. So there's as many different standards as you can think of fiber connectors that are out there. So now I'm going to talk a little bit about basic optical terms and concepts. So we'll start with optical power. So really, optical power is the brightness, the intensity of the light. So as you propagate through this, you're going to have some microscopic imperfections. You're going to have either something is not absorbed by something and turned into heat, or kind of dissipated in some way, that you're going to lose. No matter how good your fiber is, you're going to lose power as you propagate. And so the loss of intensity over distance is called attenuation. So we measure optical power in decibels, just like sound. So a decibel is 1/10 of a bell, is a logarithmic scale unit expressing a relationship between two values. So what's really important to know here is that a decibel is a dimensionless unit. It doesn't actually tell you anything. It's not a measure of brightness or a measure of loudness. It's actually a comparison. It's compared to one thing, it is this much larger. But you need to attach something to it in order to make an actual physical measurement. So for example, if you were to say minus 10 dB, that's telling you that something is 1/10 of the original signal. If you were to say minus 20 dB, that's telling you that something is 1/100th of the original signal. And another one, this isn't precise, but it's close enough for back of the envelope calculations. When you say +3, that's about double. And when you say -3, that's about half. But remember, it doesn't tell you double of what. So when you want to talk about an absolute value, you need a reference. So in optical networking, we do this as a DBM. So that's a decibel relative to 1 milliwatt of power. So if you say 0 dBm, that's effectively telling you 1 milliwatt. If you say 3 dBm, that's 2 milliwatts. If you say -3 dBm, that's 0.5 milliwatts, and so on. So if you ever wonder what is the actual correct value when you look at an optics and it says, oh, -30, and it flatlines there and it doesn't show you the actual value. The actual value, if you have no signal whatsoever, is negative infinity. But most vendors don't display that, so they have a hard cutoff where they don't show any less. But confusion between dB and dBm is probably one of the largest sources of mistakes out there. Almost always, if you call up a data center, you go to remote hands tech and you ask them to go meter the fiber, it is incredibly crazy how commonly they are in the wrong mode. They're in the mode testing loss as though they were running a cable with a known reference and not in dBm. So that's a really, really big one to be on the lookout for. So why do we measure light in decibels in the first place? So light, just like sound, follows what's called the inverse square law. So the signal is inversely proportional to the distance squared. So think of it like this. If you travel distance x and you lose half the intensity. So now you travel distance 2x and you lose another half, that you're down to 25%. You travel distance 3x and you lose another half, you're down to 12.5%. So if you use a logarithmic scale, it lets you, instead of having to do this very complicated calculation, it lets you use really simple addition and subtraction, and you can say, oh, well, distance x is 3 dB loss. And then you can just use simple addition. It makes it really easy for people in the field to do those calculations. So that's the entire reason behind using decibels. I have a table in here that shows kind of a power conversion table. So if anyone wants to look at it later on the slide deck, you can kind of have it as a handy reference, but it's easy enough to Google for too. So the different fiber optic transmission bands. So the lowest band is 850 nanometers. So that is the one that is almost always found for your multimode applications. That's your very short reach applications. It's really only used for short reach. When you start talking about fiber going across single mode or anything longer. So you have 1310, which is called O band. So this was the original band that was used. So really O band kind of covers the range from 1260 to 1360. And 1310 is the center frequency. So the reason for this is the point of lowest dispersion. So I'll talk more about that in a minute, but it's optimized for this band because it does less impairment to the signal if all you're talking about is signal dispersion and not distance. The 1550 band, which is called C band or the conventional band, and you have to be careful when you Google because there's a lot of different things that are C-band. There's a lot of different references out there. But here we're talking about 1350 to 1530 to 1565. So 1550 is the approximate center frequency. So the reason for using C-band, well, there's two reasons, right? One, 1550 is kind of the point of lowest attenuation. So if you're going for pure distance, this is almost always the band that you end up in where you're going to have the less optical attenuation. And it's also defined by the band where EDFA amplification works. I'll talk more about that later, but that's actually what defines C-band is that it's the band where you can do this one particular type of amplification. And you also have, becoming increasingly common, the L-band, or the long band. So this covers a much higher 1565 to 1625. So you kind of unlock another 16 nanometers of spectrum. And in a lot of ways, this is an extension to C-band. So you can do a different form of amplification, but in a lot of ways it behaves very similarly. So for many people who are building many new deployments, they just go ahead and do a C plus L. Or they'll do a system that's designed where you start with C-band, but you have the option to kind of bolt on an L-band upgrade. But in a lot of ways, it behaves very, very similarly. So here's a graph showing the different losses going across different parts of the spectrum and how it changes across different fiber types. So if you look at the original fibers, if you look at kind of like the early 1980s, you have these very intense peaks. So these are called water peaks. So you end up having hydroxyl molecules that get into the glass that you're not able to get out in manufacturing, and those absorb light of very specific frequencies. So you're in this like 900, 1,000 nanometer. You're in these bands that are that are very difficult to work with. And you see that as the fiber technology kind of progresses, you see much better improvements. So modern fiber these days is pretty much all, you do have a water peak, but it's much lower. So you see, this gives you a reference of, you see how the 1550, you see how the C band and L band are the points of lowest attenuation. Whereas the O band at 1310 is a little bit higher, but yeah. So the other impairment I was talking about was dispersion. So dispersion really means to spread out. So in optical networking, what happens is you have a pulse that's no longer distinguishable. You can't tell what's a 1 and what's a 0 because they've become smeared. So there's two real types of dispersion that we care about. One is called chromatic dispersion, or CD, and the other is polarization mode dispersion, or PMD. So chromatic dispersion is what happens when different frequencies of light propagate through this non-vacuum medium at different speeds. So this is actually how an optical prism works, right? This is why you see the rainbow spread out, is your different propagation, and so you literally see that signal, that white light being smeared out when going through a prism. But you see here that, you know, by the time you go some great length of distance, the different channels, the different frequencies of light have become smeared out. And even if you're inside of one channel, you know, you have one end of the frequency that you're using and the other end are propagating at different rates. It's going to be really difficult to look at this pulse and kind of determine what's going on. So historically, chromatic dispersion was one of the biggest limiting factors, and actually still is one of the biggest limiting factors for a certain class of optics. So the faster you increase your baud rate, so as you switch a signal, as you switch between 0 and 1, that's your baud rate. As you increase your baud rate, you actually increase your signal line width. So for example, if you have a 30 gigabaud signal, that's going to end up taking something like 35 nanometers worth of 35 gigahertz worth of spectrum across this channel. So what ends up happening is as you increase your baud rate, the chromatic dispersion impact is roughly squared. So you end up, you know, as you move, so kind of 10 gig was historically a big limiting factor for 10 gig. Oh, thank you. This was historically a big limiting factor for 10 gig. These days, it's a big limiting factor for a lot of 25, 50, but you're even starting to see a lot of 100 gigabaud signals that are starting to make their way into optical networking, and those are really distance limited by chromatic dispersion. And we measure chromatic dispersion in picoseconds per nanometer, so you'll see it PS/nm. The other type is polarization mode dispersion. So this is what happens when you have different polarizations of light. So remember, light's just an electromagnetic wave propagating through space. You can have it propagate horizontally, you can have it propagate vertically. And if you have something that isn't a perfect cylindrical shape, so a lot of times where you'll see this in practice, if you have old fiber that's been in the ground for a really long time, might not have been installed properly, it's been through a bunch of freeze-thaw cycles, and there's been a bunch of pressure put on it so that it's kind of compressed a little bit, you'll start to see really bad polarization dispersion, so PMD. This is what's called, the way that that's measured is what's called DGD, differential group delay. So it's the time in picoseconds between one polarization and the other, and that starts to become a problem for higher end signals. Another thing that you'll really need to know about is the OSNR, the optical signal to noise ratio. So just like any signal to noise ratio, you have a noise floor that's on your system. Now, if you're shooting a single channel with nothing else, no other light, no other anything, and you haven't gone through amplification, you probably have a very low noise floor. But if you've gone through, if you're on a mux, if you've got, if you've gone through amplification, if you've added noise, you might have a much higher noise floor. And so you're now looking at what is the amount of signal, what is the amount of clean signal that I have left compared to the noise floor of what's been added to this, and that gets measured in your OSNR. So a big thing that we work with on fiber is WDM, wave division multiplexing. So really what this means is that you have all these different colors of light, And what you can do is you can take them and you can combine them all on the same fiber. So the goal here is that this kind of works in as ships in the night. They pass each other by and they don't interfere with each other, and that's largely true. You're able to put many different signals, and they all run right next to each other on this same pair or strand of fiber. So the most basic kind of WDM is CWDM, coarse wave division multiplexing. So really this kind of means anything that's not DWDM, but the most popular meaning is a kind of a 20 nanometer spacing. So there's 8 channels. Actually, there's a CWDM bands that are around 1310. There's ones that are around 1550. I should probably update these slides because this is from like 10 years ago when the primary CWDM that you saw was around 1550. But there's a lot of it today that's around 1310 too. And it's just this 20 nanometer spacing. The reason for that is it makes it very, so the laser signal itself doesn't get any wider. It gives it the flexibility to move around. So as the laser warms up, as it cools down, it'll shift. It'll shift where it is inside that band. And by having this really wide channel, you don't have to cool the optic quite as well. You don't have to do the engineering tolerances quite as well. So that's why CWDM gets used, is it's much cheaper and easier to engineer those systems. So if you've got low water peak fiber, you unlock kind of this 1270, 1290, 1310, 1330 that historically was very difficult to work with. You also see a CWDM just used when you talk about like a 1310, 1550 splitter, but you'll see lots of other different things that are used for this. DWDM, on the other hand, is much more well-defined, and it's typically defined by these ITUT grids of specific channels. So you've got at your most basic, and you rarely see this these days, but it still exists. There's 200 gigahertz spacing, so that's about 1.6 nanometers. And that'll get you, 20 to 24 channels in C-band, depending on your particular vendor and how they've decided to use those channels. 100 gigahertz, which is still the most common. So yeah, the 200 gigahertz is that like old 2000 era tech, or it's something that's very specialized these days. But 100 gigahertz is probably what you'll see the most commonly in passive muxes. So if you're just talking about simple metro links, where you're not amplified or you're not doing anything fancy, there's still a lot of 100 gigahertz spacing stuff that's out there. And that's going to be 0.8 nanometer spacing. That's going to get you 40 to 48 channels. 50 gigahertz is what you started to see. So this was really common for commercial long-haul systems, especially over kind of from around the 2010s, right? This, what we've actually seen is that we've gone full circle from trying to get smaller and smaller channels to now working with larger channels as we're able to work with new technology that has higher baud rates. So 25 gigahertz is stuff that was, at the peak of its day when you were trying to cram 160 channels into a system, people were deploying this for 10 gig. And then as soon as we got coherent technology, which I'll talk about later, to be able to do native 100 gig signals, you started to see everything shift back. And these days, there's actually flexible systems that I'll talk more about later. So you can actually have increments like 3.125 gigahertz increments of channel width that you can arbitrarily set depending on the signal that you need to pass. So this is an example. It just kind of shows you what the different channel size comparisons look like. So if you look at you see band, the little green sliver, and you see that's going to get you, if you were talking 100 gigahertz channels, that's going to get you, or sorry, if you're talking 50 gigahertz channels, that's going to get you those 80 DWDM channels right there. And you look at that relative to the size of these CWDM channels and how large they are, kind of gives you a sense of the different channel sizes you're talking about. So what's the advantage? Like I said, CWDM, cheaper, less precise lasers. It's the signal itself isn't any wider. It's that you're able to deal with different temperature variations. With DWDM, you get far more channels. You get to stay completely within the C-band, which is the cheapest, easiest way to do amplification with erbium doped fiber amplifiers, or EDFAs. And like I said, you can also duplicate this in L-band. But some other uses, so a simple 1310, 1550, you'll see that very commonly. You take those two most common bands and you're able to just kind of split those in half. A lot of four-lane gray optics. So this is an old example from 10 gig that you could just make it 100 gig and it's the exact same thing, right? When the original 10 gig came out, it was much easier to do 4 2.5 gig channels than it was to do one 10 gig channel. So you see the same thing today. 100 gig LR4, it was much easier at the time to do 4 25 gig channels, it was much easier to do 4 25 gig channels than it was to do a single 100 gig channel. We're actually now starting to see, we're progressing to the point that you have single lambda 100 gig that's actually starting to become cheaper and easier to work with. So we're pretty much at the pricing inflection point today. And what you see now is a 400 gig optic. So like a 400 gig LR4 or DR4 or FR4 is going to do the same thing. It's got 400 gig signals. Each one is a single lambda and can be broken out. So you go through the same repetitive process as you come up with new technology, and sometimes there'll be an LR10, for example, the very first 100 gigs that came out more than a decade ago. We're using 10 by 10 internally. Sometimes you'll see 8, but 4 tends to be very common, and it aligns very well with QSFP, quad SFP pluggable optics. So that's why you see these 4-lane optics that are used. The other thing you'll see is these bidirectional, these BX optics. So there's all different frequencies. You can have them there's like dozens of different combinations. But what you end up having is a little micro mux that's built into the EDFA, or sorry, built into the pluggable optic. So you take an optic and you only need one strand of fiber on each end. So it's a really simple, easy way to kind of double your capacity without requiring any kind of real sophistication or knowledge in the field to deploy. So when we talk about DWDM channels, it's important to know the major terminology. So when we say 100 gigahertz, what we're talking about is channel spacing. So that's the center of one channel to the center of another channel. But that's not actually the width of the signal that you get. So the channel passband is the amount of signal that so typically this is measured what's called 3 dB, like what's the passband that we're able to get before we lose half of our signal. And that might be, so for example, a 100 gigahertz mux, a very common, cheap, ordinary 100 gigahertz mux might only have a 50 gigahertz passband. The other 25 on either side are really there for channel isolation. The channel isolation is how much you'll clip off of the signal that's right next to it, so that you're controlling what bleeds over into your channel. And the ripple is, when you look at the passband, it's not perfectly flat, right? There's these variations, and in certain sophisticated applications, that actually becomes a major constraining factor. So those are the major channel terminologies that you need to worry about. So the different WDM components that are out there. So the most simple and basic is a mux and a demux. So this is a really simple, completely passive, unpowered device that really just combines or splits multiple colors of light onto a single common fiber. So mux is short for multiplexer. You'll sometimes hear it called a filter or a prism. So a filter is usually how it actually works. There's different ways to implement this, but like a thin film filter is a really common way to do it. But a prism is something people intellectually, conceptually understand as splitting the frequencies of light. The exact method that's used depends on the exact mechanism of the thing. But here's an example. If you take a really cheap commodity mux and you break it apart, what's actually inside is you've got a little module that's doing all of the work, and it just wires up to all these front ports. And typically you'll see these sold as 2. So this is how you do your 2-strand transmit receive on either side, is you just duplicate it internally. So you have 2 muxes that are used in opposite directions, and they're each the exact same device, and they generally function the exact same way. Just if you put multiple colors in, it'll turn it into one common. If you put one common in, it'll split it to multiple colors. Another major thing that you'll see is an OADM, an optical add-drop multiplexer. So what's happening here is this lets you selectively drop certain channels at a site while passing a lot of other channels through. So you'll see this when you're designing optical rings, because say you've got like a 10 location ring and you want to drop 4 channels, but you want to pass your other 36 or 40 or 80 or whatever it is. You can do that with an OADM, and you can actually reuse the same channel. So if you drop channel 1 here, and then you go further down the line, you can drop it again, and you can drop it again. So you can kind of reuse these different frequencies. But a classic OADM, or what's often called a FOTM, a fixed OADM at this point, is an entirely passive, unpowered device, and it really looks something like this. So there's a device called a circulator that basically lets you, if the signal comes in one way, it goes out this way, and if it comes in this way, it goes out that way, and you put that next to a little thing. So a fiber Bragg grating is a little thing that reflects a certain color of light. So in a design like this, you connect two circulators with an FPG, and it will drop the colors of light that you have set your FPG for. And I'll talk more about the specifics of that later. So the passive optical technologies, so FPG is a fiber Bragg grating. So what's happening here is you actually etch these little marks inside of the fiber. You do this with a very powerful, very precise laser. And when you make these little etchings inside the fiber, it actually causes certain frequencies to be reflected backwards. So you use that to, like I saw in the previous example, that would make it, if you want to drop channel 1, that'll make channel 1 go back and drop, and it'll still let all the other channels go through. A thin film filter, a TFF, is what you typically see for your kind of 8 to 16 channel systems. And an AWG, an arrayed waveguide grating, is what you see for your 40 plus channel systems. And in fact, a lot of your 50 gigahertz, your 80, your 96 channel systems are actually just two different 40 channel AWGs glued together. So that 40 to 48 channel mark is pretty much what's happening here, and it's basically a prism and an interferometer. So you have these two different prisms that are connected to each other with very precisely measured lengths of fiber, and it ends up causing the light to constructively and destructively interfere with each other, so that you get these different channels that are all directed down different wavelengths. And so the original AWGs actually needed to be cooled, but the modern ones are called athermal. So you see AAWG, those are the ones that don't need active cooling, that you can just put anywhere, and that's most commonly what is the core of all of your 40 plus channel muxes. So the next thing you can do with an OADM is make it reconfigurable, or it's called a ROADM. So a ROADM is built around something called a WSS, a wavelength selective switch. So this is, and there's a bunch of different technologies inside that can make this happen, but this is effectively a thing that you can tell it, I want to send this frequency of light down this direction and this frequency of light down this direction. And you tie multiples of those together. And usually you have some amplification on the other side. So there's two really common architectures. One's called broadcast and select. So you, for example, if you wanted to go 4 different degrees, you take your signal, you split it 4 different ways, you send it out, so you didn't have to do anything fancy on the transmit. And then on the other side, you have your WSS, and you tell it, I want to accept this channel. The more sophisticated version is one where you have a WSS on both sides. So you actually control which channels you transmit, which channels you receive, and that you'll get different performance characteristics with each one. And like I said, you end up having to do some amplification because WSS is kind of a lossy event. So when we talk about ROADMs, we talk about them in degrees. So a degree is a different direction that light can be steered. So if you say, here's a 10-degree ROADM, there's 10 different ways that the signal can be steered. So like a 2-degree is the most common, where you're going through a ring, you have an east and a west, and then you have your drop. You would hear that described as a 2-degree ROADM. But they're up to like 32 degrees now, and probably even larger. There's very sophisticated large-scale ROADMs that are out there. They also tend to be very expensive. So here's what that looks like. If you look at a FOTM, what that's telling you is when you go put this in, when you go physically install the mux, you're deciding at design time what channels are going to be dropped where. So it's kind of good if you're doing very simple rings or little subtended strands, little U's and things, or you have kind of, here's a classic example, like 2 kind of core uplink sites on either end and a bunch of devices in the middle. And you can kind of get away with saying, well, I'm just going to drop 4 channels at every one. And if for whatever reason you fill up the 4 channels, then you can usually just go, oh, I'll just up my technology. I'll go from doing 10 gig to 100 gig to 400 gig to 600 gig. So you get a lot of play that way, and it lets you do these very cheap, very simple photoms. But it's really doesn't work well if you want to, if you're an optical carrier and you want to do any point to any point, or you want to have, you're 10 years down the line and the site that was nothing has now become the latest hot Equinix that everyone has to be at, and people are buying like crazy there. That's where you tend to focus on the ROADMs. The ROADMs let you dynamically connect any point to any point through software. So your NOCs can sit there with a point-and-click GUI, and they can look at where everything is going. But like I said, it's built on these incredibly complex and expensive pieces of equipment. So the ROADM has evolved quite a bit through the years. So if you look at the original ROADM, what was happening was it was reconfigurable, but it was reconfigurable, and it still went to a mux that broke things out to a fixed port. So if you wanted to drop channel 40, you sent it to a mux that split out channel 40, and you now had to plug an optic speaking channel 40 into that channel 40 port. And if you wanted to move that around, if you wanted to change frequencies, you had to go out and send a tech to move, potentially change the optic. But if you have a tunable optic that can send any frequency, you still have to go physically move the cable to another mux port. So the next thing that came about was the colorless ROADM. So this kind of eliminates the need to map any specific frequency to any specific port. So basically what you're doing here is you're sending the signal out all the ports. So you don't have that 40 channel breakout anymore. You might have like an 8 channel splitter or something, and you're sending that signal out all of the ports. And in coherent technology, you're actually able to lock on to specifically the frequency that you care about and discard the rest. So that's where colorless ROADMs came in. And then the modern technology is what's called a CDC. So it's colorless, directionless, and contentionless. So colorless means that you can drop it to a port that doesn't have a specific hard-coded frequency. Directionless means from that port, if you have multiple degrees, you can say, well, I want to send this east, I want to send this west, I want to send this north. And contentionless means you can use the same channel at different times in different ways without. So you could say send channel 40 north and send channel 40 east and send channel 40 west and not have any kind of contention or blocking happening there. So the goal here, what people are trying to do is to make it so that you can move these optical channels entirely in software. So the transponders can be reallocated. So if you've got a fiber cut, if you've got shifting time of day traffic, if no matter what your application, right, you need to quickly, rapidly provision something for a customer. It really lets you do these very dynamic changes, and you can actually react to your bandwidth capacity needs and change where you map a channel. So you might buy a transponder, but you get more than just one path out of that transponder. You get the ability to move that transponder around and potentially increase its useful lifespan and what you're able to get from its economics. And there's a system, so they use PCAP, the Path Computation Element Protocol. So there was originally an extension off of MPLS called GMPLS that did this. Now you're in PCAP, but it's basically your router is able to request. It's able to say, hey, I need more capacity, give me another channel. And you're able to work with that tunable transponder and those CDC ROADMs to dynamically respond to changing IP network conditions to change where you allocate your transponder and what you do with it. So don't underestimate the amount of complexity that this adds to your system, though. So here's actually what's inside if you were to go look at one of these CDC ROADMs. So the very first thing that you do when you come in is you have an amplifier because you're going into a very high loss event. You have like a 1/20 WSS. That's extremely lossy. So that breaks it out into all these different. So basically, you have 20 different degrees that you could send this signal, and each one will go into an amplifier array. So as you come out of this, like if you have a 20 channel WSS, you have a 20 by amplifier array that's able to amplify each one of those signals, and then that sends it down to what's called a multicast switch. So you have like a 16-port splitter, and that 16-port splitter will split this and send it all these different directions, and then that will go to the other side, and you do the same thing in reverse. And you're having to amplify loss, amplify loss, amplify loss all along the way here. So it gives you that great amount of flexibility, but at the penalty of a lot of amplification hits. Another thing that you'll see is a DWDM super channel. So it's kind of what happens if you want performance that a single carrier can't deliver. What you can do is pack multiple carriers together in a single channel. So the reason for that might be that you're doing it in some way that might be tighter than if you were to use a standard channel size. So in this example, like what would happen if you wanted to deliver a terabit using off-the-shelf technology? A 375 gigahertz system, 320 gigabaud. Like we are not there. We have very, very good technology these days that's up in the 100 gigabaud plus, but we're nowhere near that yet. So this would be practically impossible to build. But something that was much simpler and easier might be 260 gigabaud channels and a dual carrier inside of one super carrier channel. Something that was entirely possible to build almost 10 years ago at this point, maybe 8 years ago at this point, was 10 32 gigabaud, actually no, more than 10 years ago, you were able to build a terabit by using these 10 different lasers, these 10 different signals at 32 gigabaud, all combined and packed really tightly in 375 gigahertz of spectrum. And that changes over time as the technology gets better and better, but that's an example of where you were able to pack those channels very tightly and get kind of good efficiency out of it. So the DWDM channel size has really evolved quite a bit. So if you look at the simple passive designs, they're all very hard-coded. They're all very much set around, well, there's going to be a 100 gigahertz space channel or 50 gigahertz space channel. So no matter what you send down it, if you're sending a 10 gig signal that is kind of narrow, or if you're sending a 100 gig signal that's much wider, you've got the same amount of channel size, and so there's potentially some waste in there. With a modern system called FlexGrid, you have the ability to kind of dynamically tune your channel. And really what's happening in FlexGrid is it's attached to a ROADM. So this WSS that is deciding what channel to send where, it's deciding what to call a channel at the same time. So you get this flexibility where if you have these very narrow channels, you can have them use a very small amount of bandwidth. If you have these very wide modern channels, you can have them allocated on a single channel, but it's really attached to a ROADM. So it comes with all of the overhead associated with going through a ROADM. So a bunch of other optical networking components. Dispersion compensation. So you'll see this called a DCU or a DCM, dispersion compensating unit or module, or sometimes DCF, dispersion compensating fiber. So originally what this was a big spool of fiber that was designed to cause dispersion in the opposite direction of the transmission fiber. So you run it through 80 kilometers of line fiber, and then you run it through a spool of fiber that's designed to kind of compress it the other direction. So you kind of add like 20% overhead to a signal, to a fiber span, but you'd put this in your amp site, and it was how you corrected for dispersion. The newer designs were all based on fiber Bragg grading, so you can actually have an FBG cause dispersion in different ways as it does its reflection. But that actually is very specific to specific channels and specific channel widths. So a lot of systems actually kind of move back into the dispersion compensating fiber. You'll see both used depending on what technology you're working with, but there's different reasons for working with different ones. An optical switch is basically something that lets you, there's little micro mirrors that let you move a port assignment. So without having to do you don't have to take an optical signal, turn it into electrical, then re-encode it in optical and retransmit it. If you have something coming on port 1 and you say, I want to send it up port 7 now, you can log into a device and request that it move these little micro mirrors and change this around. So really the most common applications for these, a lot of optical cross-connect systems. So if you've got a very high-end carrier or data center that doesn't want to go out and dispatch people to move cables, you can do this. But probably the most common application is lab environments, right? Where you're frequently remapping and reassigning ports, and you want to be able to do that without the potential downside of tangled cables, cleaning the cables, like sending someone out to move the cable. Because they're so expensive, they tend to fall into that environment where there's not a lot of them, but they're able to do that work in the lab. A WSS, as I was talking about earlier, is something that lets you steer wavelengths. So the first generation designs were these 3D MEMS, these little micro electromechanical devices that move mirrors around. The modern ones are actually kind of based on liquid crystal and silicon, so kind of the same tech that was in old projection TVs. You're able to steer the frequency of light around and get it to bounce off in a certain way and behave a certain way that you want. But that's what's inside a WSS and why it tends to be very expensive. A circulator I talked about earlier, it's something that's not really seen by an end user, but it's that if it goes out port 1, it goes out port 2. If it comes in port 2, it goes out port 3. So it lets you, you know, in this example, it lets you build these very simple OADMs and things like that with simple like FPGs. Optical splitters pretty much do exactly what they sound like, right? They split a signal. So most common examples you'll run across a 50-50 splitter. This is very commonly used for optical protection. So imagine you've got 2 fiber paths and you want to protect all of your signals in the cheapest, easiest way possible. A really easy way to do that, split the signal in half. So you literally send the same light out both directions, and then you have another device on the other end that looks at it and says which signal is the strongest. And if the light drops from one, it'll switch to using the input from the other. And you're able to protect, you know, you can protect hundreds of channels worth of systems with this very simple, very cheap, couple $100 device at the penalty of like a 3 dB splitter and a little device on the other end to look at optical power levels. So that's very commonly used. You'll also see like a 99.1 or a 98.2 or a 95.5 splitter used for what's called OPM, optical performance monitoring. So if you've got a complex commercial WDM system, you can take the signal, split off like 5% of it, and send it to a little spectrum analyzer. And that can look at it and tell you how each individual channel is performing. It can look at the noise, it can look at the individual channel. It's a good way to kind of diagnose this large complex thing that's operating in the field, and you'll use a little splitter to do that. You'll also see this used for example, cable TV distribution, right? So, or your PON systems. So if you look at a passive fiber network, you might run it through a 1x16 splitter or 32 splitter. You literally take the same signal and you just split it 16 or 32 different ways, and you send it out to all of those destinations, and then you just select the content that you want on the other end. So that's behind all those kind of PON systems. So now I'm going to talk a little bit about optical amplification. So optical amplification is the ability to increase the intensity of a signal without having to decode it, figure out what the signal was electrically, and then re-encode it. So it's no regeneration. And there's different types. They have different properties, and they're used for different frequencies of light. But really, the basic ones that you'll talk about are the booster, the preamp, and the inline. So a booster is something that's designed to take, you kind of use it at transmit. So you take an already pretty strong signal and you make it even stronger. You want to get it as hot, as strong as you can possibly get before you send it out onto the line. Preamp is something you do on the other side. It's something you do before you decode the signal. So you've got a very weak signal in, you want to boost it up a little bit so that you're able to decode it easier, but it's balanced in the way this design is designed to work with a low intensity signal and just make it a little bit brighter. And then an inline amp is something that kind of strikes a balance in the middle. It's something that you might put, so if you've got multiple regeneration sites or multiple amplification sites along the way, you might have an inline amp that's kind of designed to work with both. So the EDFA, the erbium doped fiber amplifier, is the most basic, common. This is what makes up almost all amplification that you'll run across on a day-to-day basis. So what happens here is you have a little spool of glass. and it's doped. So when they make the glass, they in the chemical mixture of the silicon, they put a little bit of different chemicals in, and they put these erbium ions in. So you have this erbium 3+ ion that you put, in the parts of like 1 per million or whatever. I don't know what the actual ratio is, but you put a few of these into the glass. And so it's what's called a lumped system. So the amplification happens inside of a box. When low signal comes in, by the time it leaves, it's much brighter. Everything happens completely inside of the box. So inside the box, there might be like a 10-meter spool of fiber, or 15 or something. It's relatively short. And you take this doped fiber and you inject a pump laser. You use a different frequency of light that has nothing to do with your communication. So in this case, there's two that we work with, 980 and 1480. So 1480 will get you to that quasi-stable state. It'll basically, when it comes in, it hits those erbium ions and it makes the electron jump an energy level. It jumps up to a higher shell, higher orbital. And you now have a certain amount of time for a photon to come in, and a photon of a certain specific frequency. It comes in and it hits that atom that's had its electron jumped up to a high energy state, and when it does, the electron decays to a lower state and it emits a clone of a photon. So same frequency, same direction, same spin, same everything. It's a clone. So that's how you make the signal brighter. And different elements will do this for different frequencies of light. So we use this particular erbium configuration because it works with this frequency, this band that is very applicable to what we do for transmission. And so the 980 and 1480, if you want to pump a lot of extra power into it, you might use both. Or if you've got a cheap system, you might only use one of those. So what happens is you look at this and you go, well, okay, I made the signal brighter. Can I keep doing this forever? Like what's the limiting factor? So the limiting factor is what's called noise, or ASE, amplified spontaneous emission. So basically the physics here is that once you pump that electron up to a higher level, you have about 10 milliseconds for a good photon to come in and hit it. And if in that 10 milliseconds nothing comes in and hits it, what'll happen is it'll spontaneously decay and it'll emit a photon, but it won't be the photon you want. It'll be junk noise photon. So you've now added noise to the spectrum. You've irrecoverably added noise that you're now never able to remove. And that's what's ultimately going to be the biggest impact to your ability to do this. So if you look at this little graph, this shows you, this is what a kind of a common EDFA noise level looks like. So there's certain channels that are much worse than others. You see there's two real channels here, and then there's this noise floor going across C-band that has been created by this EDFA that didn't have a strong enough input signal. So the reason that I talk about this is, I probably need to find a better way to show this graph, but so what I'm trying to show here is what happens if you amplify at different power levels. So if you've got a really bright signal coming in already, it's much easier to not emit noise. It's much easier to not have that spontaneous emission. If you've got a very weak signal, it's much easier to cause noise. So this is what happens as you go through, if you were to go through 10 EDFA hops where you only allow, the signal comes in at -5 dBm before you amplify it, you'll see that you sit at almost no loss in your OSNR. It's impractical to do that in a modern world, but that's showing you what happens. Whereas if you go to the far end and you allow the signal to fall all the way to -25 dBm before you amplify it, you see that you get this very quick drop in OSNR, and that's ultimately what limits your ability to take a signal and kind of do long distance with it. Oh, that went a little crazy. It just did a whole bunch of advancing. Sorry, let me try and get it back. Okay, so another type of amplification is called Raman. So this works on a principle, something called stimulated Raman scattering, which is actually, in some conditions, an impairment that you don't want. But in a particular case, you can use it to cause amplification that you do want. So instead of an EDFA being a lumped design where everything happens inside of this little box, Raman is a distributed design, almost always. So really the way to use it best is what's called counter-propagating. So imagine you've got your actual signal coming in that you care about, and you pump a laser of a different frequency of a certain specific frequency of high power going the other direction. And when those two interact with each other, the Raman effect causes the power from the one frequency to drain and the power to be transferred to the other frequency. So the pump laser, the amplification laser, you filter out on the other end. You don't care about it. It's literally just there just to transfer power. But what happened was the signal that you did care about has now become brighter. And if you use this counter-propagating, so you launch it the other direction, what happens is it comes in much brighter. So here's an example of what this looks like when you talk about an EDFA-only system, right? So the two things you want to avoid, you want to stay out of really high power areas. So this is where you get your nonlinear effects. And you want to stay out of very low power levels. This is where you start to add noise. So if you wanted to stay out of the red and the orange zone here, you might have to have much smaller hops. Or different designs, but this is kind of what happens in an EDFA-only system. In order to close the gap between these two hops, you had to be into this high nonlinear band you didn't want to, and you had to let it fall into this high noise, low power level that you didn't want to. So in an EDFA Raman example, where you now add a Raman pump propagating back the other direction, you're able to start with a launch power that's much lower, so you stay out of this nonlinear effects zone. And by the time it starts to come in, you see it just stops getting weaker and it turns around, it starts getting brighter. So by the time it comes in, it's already a lot brighter than it was before than it was along its travel path. So now you're able to stay very well out of this high noise zone. So now you're able to use a smaller EDFA that will add a lot less noise, and this results in a dramatic improvement in performance when you're talking about long-haul systems. So how much? So here's an example. Let's say that you wanted to hit a floor of 21 dB OSNR. So like that today I would get you, maybe a 300 gig or 400 gig, depending on your configuration. That will get you, let's say this 400 gig signal that you wanted to send it. If you are doing an EDFA-only system, you might only be able to do 7 hops. So if we were to say 100 kilometers each, which is already very aggressive, right? This is brand new, clean fiber with very low loss that you're able to get this 100 kilometer span, but we'll use it for the simplicity of math. You might have been able to get this 400 gig signal to only go 700 kilometers. When you do hybrid EDFA Raman, you're now able to get this same signal to go 2,000 kilometers. So you see that you're able to get much more efficient use out of this transponder. And the transponder is like I said, that's where Moore's law lives. So that's the part that you're going to pay what you're going to pay for it, and it's just like buying a computer. It's a rapidly depreciating asset, right? Because you're guaranteed that over time it's going to become worth less and less as something better and better comes along. So your job in designing a system is to take full advantage of the transponder that you just bought to get as much capacity out of it for as long a lifespan as possible. So when you put that on an EDFA Raman system, you're able to get higher bit rates out of that same transponder, which you're going to pay the same for whether it's working in 100 gig mode or 400 gig mode. So that's why you design systems where you really want high OSNR. But amplifiers introduce some of their own issues. So a big one is power balance. So what ends up happening is if you have one channel that is significantly brighter than another than others, and you run that through amplification, that bright channel is going to suck up all of the amplification power, and it's going to result in this great imbalance. So the other channels are not going to get amplified as much as you want. So there's ways that we deal with this. So the most common way is what's called a GFF, a gain flattening filter. So this is pretty much inside of every EDFA. There's a filter that's been designed to pretty much match whatever the output. So like if you actually look at what comes out of the raw EDFA process, you have that curved shape that we showed earlier from the noise. And you have a GFF in front of it, or at the end of it after it comes out, that takes that and kind of tries to passively flatten it as much as possible. And then even when you do that, you still end up with these variations that build up over time. So at a certain point, you need to do what's called DGE, dynamic gain equalization. And typically, you see ROADMs used for this. So you might, every like 5 hops or 7 hops or something like that, you might have a ROADM, even if there's nothing to actually steer, even if there's not another direction, you'll see people go and put a ROADM in, a certain number of hops in, because it's doing that dynamic gain equalization and preventing those things from building up and getting out of balance. Amplifiers also have limits on their total system power. So not only what they can output, but what they can take as an input. And this is really important to understand when you start talking about amplification, and probably one of the biggest areas that people don't, when they try to move from a simple passive system into using an amplifier, they don't really understand how that works. So let's consider an example. Let's say you've got a single channel that's 0 dBm, so 1 milliwatt of power. Well, now you've got a 40 channel system. So now you've got 40 of those, 40 milliwatts of power. So what is that? That is plus 16 dBm. So if you run this through an amplifier that has a maximum input power of -6, you run all 40 channels through it. That means the channel must, absolute must, be below -22 dBm in order for this amplifier to not be overpowered. So as you add channel count, you end up with the amount of power per channel going down, or ultimately what limits an amplifier is the amount of total output power. So a really basic, cheap Metro design might be plus 17 dBm. A more expensive long haul or Metro system might be plus 20. A really expensive long haul system might be plus 23. But those are kind of the limits. So if you talk about, well, I can only output plus 17 of power, and I've got 40 channels coming in this example, you needed to be below -22 dBm, and we already saw how far that puts you into the noise floor above, or in slides earlier. So if you look at the other thing you have to think about is this will change dynamically as you add channels. So imagine you've got, for example, the power goes out in one of your sites, and all of a sudden a bunch of channels go offline. Well, what ends up happening is the power that was being distributed across all those channels is now available to make the other channels that are still there much brighter. So you end up having to have a system that is aware of this and reacts to this and tunes dynamically. Or a really common example where people don't think this through is they go and turn up some new channels, and all of a sudden the old channels stop working because you've taken the amount of power that was going to those old channels and distributed it across a larger set. So some more optical networking concepts. Forward error correction. So FEC is something that adds this extra redundant information to your transmission, so basically you can computationally recover from any errors. So the way this works in practice is it lowers the required OSNR for you to get a usable signal. So for example, you can take a 10 gig Ethernet signal, right? So 10.325 is what it is by the time you add all the overhead. So say you pad that 7%, you pad that to 11 gigs. That'll let you take a signal that used to only be receivable at 80 kilometers and take it out to 120 kilometers, and you'll still be able to receive this lower power system that would have been too noisy to work with before, but because you're able to recover some of that loss through FEC, you're able to take it out to 120 kilometers. So this really becomes important when you start talking about upgrading old WDM systems, because it's usually not practical to go move an amp site, right? This might be $1 million sites deployed in a cornfield somewhere with a land lease that you don't have the flexibility to go up and move it to change the distancing that you want. But if you use FEC, you're able to keep working with these distances that you need to work with. So there's a couple different generations. So the most basic FEC, RS FEC, Reed-Solomon FEC, is your first gen, so that gets you like this 6% overhead. Second gen, kind of EFEC, is the 7% overhead for 8 to 9 dB. And then the modern FEC is up into the 25%, so SD soft decision FEC. So it's FEC that doesn't have to tell you the answer is definitely 1 or definitely 0, but it points it more in the direction, and then it lets the rest of the system figure out what it is from the other inputs. And so you might look at this and go, well, why do I want to put 25% overhead for just a couple of dB gain? Well, remember, if you add 2 dB of OSNR tolerance, that can be worth hundreds of kilometers. That can be worth a tremendous amount of money in terms of transponders. So FEC is now really an essential part of everything that we do. I don't think there's a single, it is definitively baked into every new 100 gig service beyond like the original LR4s and ER4s. It's baked into SR4. It's baked into all of your 50 gig, your 100 gig signal lambdas, your 400 gig, your 800 gig. It is inherently a part of every modern system. Is that we take full advantage of FEC because it really is a tremendous improvement. So here's what that looks like in practice. So you see that where if you were, this is the bit error rate, so the BER. So as it goes down, you get progressively more and more and more exponentially increasing amount of errors to the point that you would create something that would be very unhappy. So you were before, if you were if you wanted to be at this 10 to the minus 15 worth of bit error rate on a non-encoded signal, you might have to have an 18 dB OSNR. And with a really, really well-encoded FEC signal, you might be down into the, if you're at 9, you're able to get that same level of performance. But it tends to make systems, you see this kind of cliff. This is kind of the behavior that you get where things will be working great, they'll be working great, they'll be working great, and all of a sudden they'll fall off the cliff. So when you look at a system and you want to figure out, like, how is this thing working, you look at what's called the prefec, the prefec bit error rate, and you're able to see how much FEC is saving you. Another thing that you'll see is OTN digital wrapper technology, G709. So this is kind of the modern replacement for SONET and SDH, where you're able to take a variety of different signals and transport them across an optical platform in a way that is really generic to the protocol. So, it might be GigE, it might be 100 GigE, it might be fiber channel, it might be any number of different technologies that are out there. You can wrap them inside of OTN, and the OTN framing will let you do. It behaves in a lot of ways very similarly to SONET and SDH did, but it lets you work at an optical level with all these different protocol types. All right, so now I'm going to talk a bit about the different types of single mode fiber. So we already talked about how it's used for all of these long reach applications, but there's also a lot of different types of single mode out there. The most common types, so you've got your standard SMF. So this is what's called ITU-T G652. So the modern G652, I think D, I don't know if E's out yet, but so G652D, this is your low water peak fiber. This is fiber that is full spectrum. So the original, the most common stuff that's out there is SMF28, Corning SMF28 is a brand name, but you'll hear it called that. That's all your G652 stuff. Other types, you've got G653, which is dispersion shifted, which I'll talk more about in a second. You have cutoff shifted, low loss fiber, you have non-zero dispersion shifted fiber, you have bend insensitive fiber, you have fiber that lets you flex it and not cause impairments. So the standard G652 is, so the original G6, this is the kind of cable that was deployed all through the 90s. Like I said, you'll hear it called SMF28 just because that was a really common brand. It was the early Corning brand, probably makes up the bulk of the fiber that's out there. But you can also call it NDSF, non-dispersion shifted fiber. So this was fiber that was really, like I said, optimized for 1310. It has the lowest rate of dispersion there. And it was actually designed before WDM was a thing at all. Interestingly, WDM is a relatively recent invention. It was only invented in the late 90s. So a lot of fiber that was deployed predates even the concept of this. And ironically, we've now come full circle to this actually being the kind of fiber that we want to work with. Now, you want to work with like the modern version, the G652D, but it's become the kind of fiber that we want for modern high bandwidth systems. Like I said, here's the modern version of it, is what's called low water peak fiber. So remember we talked about the different rates of absorption at different frequencies. Here's what it looks like when you look at absorption of light by hydrogen that's inside the glass. And so by designing the fiber a little bit better to higher standards, you bring that water peak loss down and you make those bands more usable. So dispersion shifted fiber is interesting because what happened here was they said, well, can we redesign the fiber in such a way that we move the point of no dispersion that we see down in that 1310 range, can we move that to 1550 so that we get low chromatic dispersion and low attenuation, right? That was the goal. And they designed this, once again, they designed it and deployed it before WDM systems of any kind were a thing. And then it turned out to be a really bad idea. Because when you have no dispersion and you start doing multiple channels, the channels interact with each other much easier. And so this basically, as soon as you start talking WDM, as soon as you start talking more than a single channel, something of actual zero dispersion becomes practically worthless. So the fiber that was deployed of this is all gone and basically unusable at this point. So then they said, all right, well, can we find the best of both worlds? Can we make it so that we're able to get low dispersion, not zero, but can we get low dispersions? Can we move the point of zero dispersion just outside of what we're working with so we have less dispersion? And like I said, dispersion was originally a big limiting factor. If you look at like what constrained us at 10 gig, in by 10 gig signals for the longest time, it was chromatic dispersion. It's still one of the things that constrains us quite a bit today. So you made, well, like I said, you have fiber with different slope. So you might have your transmission fiber that the signal spreads out a little bit this way, and then you have fiber of a different slope that's designed to recompress it when you come through and you need to dispersion compensate. So this kind of worked, but it still is not the fiber that we want to work with today. It turns out that dispersion that was originally the biggest impairment for the kind of basic bright dim signals is actually desirable, especially for high bandwidth coherent systems. I'll talk more about that later, but you want the signal to be spread out a little bit. Other fiber types, so G654 is what you see for high power subsea cables, and they'll design it so, let's say for example, you don't care about carrying 1310. You want a fiber that is really specifically designed for like your C/L band with really high power. You'll have different core sizes, different design criteria that go into it, but it's something that's very specialized where you start to trade off some of the things that you wanted in traditional fiber for fiber that lets you work with very specific, very long reaches. G657 is your bend insensitive fiber, so it's maybe not insensitive, but it's greatly reduced sensitivity. So it's you use a much higher refractive index cladding, and you're able to work with a fiber and bend it and not have it knock out the signal. So here's an example of the different dispersion rates of different commercial fiber types that are out there. So you see the classic number for C-band, the average number for like G652 is 17 picoseconds per nanometer. But you'll see that that's across C-band, it actually varies quite a bit, right? There's a lot of slope to that. So there's three of the most common, so Leaf, True Wave, Terralite, there's these different G655 fibers. You see that they're much lower, and they've moved this point of zero dispersion outside, so that's where that's the non-zero dispersion shifted fiber. But they each have different slopes, and so when you go to counteract that dispersion, you have to be aware of what the fiber type is and make sure your dispersion compensation matches that exactly. So now I'm going to talk about nonlinear impairment. So this is if you ever need to wonder like what's nonlinear, what's happening, think of it as high power problems. If you don't transmit at high powers, you will never see these problems. Well, what do I mean by high power? Well, the answer is it depends. It depends on the signal. It depends on how tightly they're packed. It depends on what the exact impairments are. But as a rule of thumb, as long as you're below like +4 dBm per lambda, you're generally pretty safe. As you start to go above that, as you start to go, well, why can't I just transmit a +10 signal? Well, it could go wrong. Then you start to hit these. So the most common impairments, they're broken down into the stimulated scattering, so stimulated Brillouin scattering or SBS, or in stimulated Raman scattering or SRS, and then things that happen because of the Kerr effect. And what happens here is very intense light actually causes the effective refractive index of the fiber to change. So you get three different ways that this goes wrong: 4-wave mixing, self-phase modulation, and cross-phase modulation. where it's basically, I'll talk more about each one. So SBS, stimulated Brillouin scattering, is kind of the first one that you'll hit. So as you start to turn up the power more and more and more, what ends up happening is if you look at a molecular level, the glass that makes up this fiber is actually vibrating. And it is basically the same effect as a standing wave, like when you pluck a guitar string. You end up building a way that because they vibrate in a certain pattern, it actually ends up reflecting the power back. And so what will happen here is you can actually cause damage to your transmitter by having high amounts of power reflected backward, because the fiber simply isn't able to, at an atomic level, take that amount of power in that exact instant that it passes through it. So the way to think about it, like I said, is power density, right? So as you have a wider line width, if you have a high gigabaud signal that is a much wider line width, you actually spread that power density out, because in any one exact fraction of a second, the optical power is a bit more spread out in terms of how it propagates. You actually this is where you want dispersion, because dispersion causes what used to be everything lined up in one exact instant to kind of smear out. So you spread this power level out so that any one instant it's not all landing on one exact atom. But SBS is well, that pretty much sums up. So SRS, Raman scattering. So we talked about before, this is the effect that caused power to transfer from a pump laser to the signal that you actually want. But what happens here is if power transfer happens in a way that you don't want, and the interesting thing about it is it actually is greatly affected by how tightly you pack the signals. So if you have let's say an 8-channel count system, and you have 50 gigahertz spacing, so you pack it very tightly, you're able to go to plus 21 dBm. You're able to go to these incredibly high powers. As you add more channels, this becomes a bigger problem. So as you add total channels, if you now go to an 80-channel system, you are now limited to, say, for example, 0.5 dBm. Or if you're 100 gigahertz spacing and you're at 40 channels, you've got a limit of 3.6 dBm per channel, or per lambda. And as you go above that, this is what it's like in 655, so this non-zero dispersion shifted fiber. As you go above that, you start to see power transfer between wavelengths that you don't want. So all the Kerr effect ones, 4-wave mixing is what happens when you have these regularly spaced signals. So say you've got 3 signals right next to each other that are very bright, high intensity. What ends up happening is they interact with each other and they create harmonics. So you'll create noise that you don't want on the actual channels themselves and on all of the surrounding channels. So like I said, low dispersion fiber, really low dispersion is what causes the vast majority of these effects, but it depends on how tightly packed they are. So in this example, the closer they're packed, the worse it gets. In the other example, the closer they're packed, the better it gets. But this is irrelevant of transmission, right? This could be a terabit or a megabit. It's an optical level effect. But here's why we talk about dispersion and what matters, right? So if you look at something of 0 picoseconds per nanometer per kilometer, so this is your rate of dispersion, and you look at like how easily will it mix. This is what's called mixing efficiency. If you have no dispersion, it's incredibly easy. You have to go to very, very wide channel spacing in order to start getting away from being incredibly easy to cause 4-way mixing. Even adding so much as a single, like even adding 1 picosecond per nanometer per kilometer greatly improves that. But then if you look at kind of modern, old fiber, classic SMF, like SMF28, which has now become the desired standard for modern fiber, you see how much greater it is able to tolerate that by keeping that higher rate of dispersion. Yeah, I'll skip over some of the, like you can look at this and look at a table if you want to look at it in the future. So the other things are inter-channel effects. So XPM, cross-phase modulation, is what happens when one wavelength of light affects the phase of another. So this is what happens when you mix NRZ and coherent systems. So if you've got an existing WDM system with a couple 10 gigs on it that are old signals, and you go, oh, I want to put a new 100 gig coherent system on it, and you put them very close to each other, you're going to get a high XPM penalty. You're going to get the old signal is going to cause impact to the new coherent signal by changing the phase, which is very important in coherent. And then SPM is self-phase modulation, and that's basically when the difference in power, or the power level between a 1 and a 0 is so strong that it actually causes the same kind of curve effect. So nonlinearities, like I said, it's all about energy density. Higher chromatic dispersion helps that spread out. The other thing you can do is you can have a larger fiber. So in fiber, we call this MFD, the mode field diameter. So it's basically the surface area over which, in the core, you're able to spread this fiber out. So the fiber's effective area, if you're already able to find that in the spec, you can take the mode field diameter and then use pi r squared, greatly affects the amount of power that you're able to put in. And so if you look at like leaf fiber, for example, that actually stands for large effective area fiber. That was an attempt to make NZDSF fiber that had a larger effective area so that you could mitigate some of these effects. And if you look at like submarine fiber, like Corning Vascade or something like that, you have these very, very large effective areas. You push these things out as far as you can go so that you can put high power in. But the one trade-off here is that the larger the effective area, the less Raman gain you get, because remember, the Raman gain that we're getting from Raman amplification is the exact same Raman that's happening when you don't want it. So what do we actually transmit over these fibers? So at the end of the day, remember, we live in an analog world. Digital signals are still being encoded, analog waves, and light's just another form of electromagnetic radiation. So the simplest form of modulation that we work with is what's called IMDD. That stands for intensity modulation with direct detect. The specific variant of that we most commonly work with is called NRZ, which is non-return to zero. And all of this is what's called ASK, amplitude shift keying. All of this is a fancy way to say bright for a 1 and dim for a 0. And direct detect means there's a photodiode and it's looking at it and detecting how quickly it goes bright, dim, bright, dim, bright, dim. And that is the limiting factor. So most of your client optics, almost every client optic you'll work with, especially the older systems, are all NRZ based. Everything 10 gig and below, certainly. So like I said, this is baud rate. So as you modulate the signal, as you go between bright, dim, bright, dim, bright, dim, that's your baud rate. So baud is your symbol rate per second. So a 10 gigabit signal actually runs at 10 gigabaud, so you get 1 bit per symbol, 10 gigabaud, so 10 billion times a second you flash bright dim, bright dim, bright dim, and you're able to look at that and decode and get your 10 gig signal. So that works really well to a point, and like I said, the impairments are basically the square of as you raise the baud rate, the impairments go up dramatically. So 10 gig was definitely the big limiting factor for quite a while. These days we're able to work pretty far with 25 gig, but even as you go 25 gig and above, you're able to get to this 20-30 kilometer range without a real problem. But as you start to look at 40 kilometer, 80 kilometer optics with NRZ kind of signals, you're very much constrained by the chromatic dispersion in these high baud rates. So where do we go from there? What's the sad internet to do when the baud rates stop keeping up and we can't spread our cat videos? So where you go with this is you go, oh, how do we increase the amount of information? How much information can we encode per symbol change? So there's two ways to do this. If you look purely in amplitude modulation, you have more than two states. So instead of having bright and dim, you now have a bright and a really bright, and a dim and a really dim. The other thing you can do is what's called phase shift keying, and you modulate on another property of the signal, which is varying the phase of the signal over time. So what do I mean by improved amplitude shift keying? So another word for NRZ is PAM2, so pulse amplitude modulation 2 levels. So that's literally bright dim, 0, 1, 0, 1. A modern thing that you'll see becoming pretty deeply important in 400 gig and above is PAM4. So this is the same thing as NRZ, but there's 4 different levels. So for each change, you're able to encode 2 bits per symbol, and you're able to double the amount of information that you carried per baud rate. When you look at phase shift keying, what you do here is, if you think about an analog signal as a sine wave, what you can do is you have the sender and receiver agree on a specific frequency. So you say, I want to look at this specific frequency, and on the receiver, you have a little laser oscillator just like you do on the transmitter, and you dial it to match exactly the frequency that you're expecting to get from the transmitter, and you look at variation in phase. So you take that sine wave and you just shift it back and forth in its phase, and you're able to encode information in that in addition to making it brighter or dimmer. That's phase modulation. So that really leads us to a set of technologies called Coherent. So what is Coherent? Basically, it's the introduction of phase shift keying. So it's named after an optical property, the ability to track its phase coherence, the ability to track phase changes. So like I said, it adds that local oscillator. And it uses a laser on the receive side of the signal, and you now, by having that reference, you're able to compare and figure out what the phase variant is as you modulate it on the transmit side. But that's not as easy as it sounds, right? So this was really impossible to do with a photodiode, and it doesn't happen until you start to look at more sophisticated technologies like DSPs. So a coherent system is really built around a DSP, a digital signal processor. So this is, the same level of sophistication that goes into a modern processor in your CPU, for example, is now being custom built and designed for these signal recovery systems. And there's a lot of sophistication. There's millions and millions of transistors that are going into these very complicated pieces of technology that are really designed to recover computationally what's happening. But without that, there's no other way for this to work. So when you looked at before we had coherent technologies, we were kind of limited. We had 160 channels of 10 gigs. So we had 1.6 terabit. The release of coherent technology, the very first release, got us to 96 channels of 100 gigs. So it got us from 1.6 to 9.6 terabits effectively overnight. So that was around your 2010, 2011 era. And it's enabled all of the modern high bandwidth systems ever since. But where do you go from there? How do you keep going past PSK? Well, you can do PSK and ASK, and that's what's called QAM, quadrature amplitude modulation. So not only are you modulating the phase, but you're also modulating the brightness, and you're able to add more and more and more possible states. So this goes up, 8 QAM will add a third bit, 16 QAM will add another, 32 QAM will add another, and we're pretty commonly doing 64 QAM these days on optical systems, and eventually it'll get higher as the sophistication increases. Another thing you do in coherent is polarization multiplexing. So remember, light, just this electromagnetic wave propagating through space. You can have a horizontal and a vertical propagation, and they don't interfere with each other. So you can basically double the amount of capacity by using these 2 different polarizations of light, and you use the DSP to decode that and take advantage of that to encode data. So what you end up working with is this big table that's basically the multiplication of your number of polarizations times your baud rate times your modulation. So here's an example of kind of the most common things that you'll find out there. If you wanted to send a 100 gig signal, a really easy common way to do that is to send a 32 gigabaud signal with 2 polarities encoded with QPSK, which gets you 2 bits per symbol per hertz. So you only need a 37.5 gigahertz channel, and you only need a 10 dB OSNR, and this probably gotten even better since I wrote these slides. But you're able to take this 100 gig signal. You've been able to take a 100 gig signal and shoot it, transcontinental across the US for a decade now. But if you look at the higher end ones, you look at, well, what does it take for me to get 600 gig lambda? Well, to do that, you might need a 64 gig baud rate with 2 polarities using 64 QAM, and that's going to require a 75 gigahertz spaced channel. So the raw bandwidth by the time you add FEC ends up being 768 gigs, and all of that will deliver you a 600 gig lambda, but it's going to require a 25 dB OSNR. So like I said, by adding a couple of dB OSNR, you can dramatically improve the amount of efficiency you're able to get out of your transponder. So modern systems, this is like a 5-year-old system at this point, but all modern systems work by having a lot of options to choose from. So there's a lot of different ways you can go about getting to a signal, right? So you can have a higher baud rate and a lower modulation, or you can have a higher modulation and a lower baud rate. And there's even more sophistication than this in even more modern systems. Well, let's look at this as an example. Let's say, what happens if we want to, what are the 2 ways to get to 200 gig? Well, one way is a 32 gigabaud signal at 16 QAM. So that requires a 19.5 dB OSNR in our example of our particular DSP, but it fits in a narrow channel. It fits in a 37.5 gigahertz channel. So you need something that small to go through a classic 50 gigahertz ROADM, because by the time you go through the ROADMs, it starts to clip the edges a little bit. So that's about the widest signal you would get in an old, if you're running a 10-year-old ROADM system, which is still very common in the carrier world, that's the most amount of capacity you're going to get out of that in terms of passband. But it's going to require a higher OSNR. But if you're able to trade spectrum, if you're able to go, well, I can work at a higher baud rate, I can work at 64 gigabaud. Now, in order to get 200 gig, I can go down to QPSK. So I only need 14.5. So basically, I've improved by 5 dB the OSNR that's required to do this. And the trade-off I made was that I needed a 75 gigahertz channel. So that's where you see there's a lot of variation that's happening, where you still have support for things that are brownfield deployments, but more and more and more you'll see things moving towards higher and higher baud rates and thus wider channels as you deploy. So the other big advantages of Coherent, Coherent is very, very good at dealing with dispersion. So CD, chromatic dispersion, you'll be able to work through hundreds of thousands of picoseconds per nanometer instead of thousands, and not care. In fact, it actually makes coherent systems work better to have more chromatic dispersion than less. And like I said, Coherent can actually lock onto a specific frequency. So you in some cases you don't even need a mux. If you only wanted to do like 4 channels, you can take the signal and put it into a simple 4-channel splitter, which is incredibly cheap, and just plug them into 4 different channels, and you'll never need to do anything else. You're able to have the receiver lock onto just the channels that it cares about. The downside to this is, of course, this big, expensive, power-hungry DSP that's very complex and has historically been very difficult to integrate into pluggables. Which brings us to 400ZR. So 400ZR is modern coherent in a pluggable in a way that's actually like highly disruptive to traditional systems. So historically, coherent has always lived in these external transponders because you were chasing spectrum efficiency. You're designing this to sell to a big carrier that's trying to, in their mind, they're able to sell 80 channels of transport, and if they need to sell 81, then all of a sudden they have to go out and double their costs because they have to go double the amount of amplifiers at every site. So they're trying to be very spectrally efficient. Whereas when you look at what will work in a pluggable, you're actually caring about space and power efficiency. So what would have lived like a 1U box that could take a couple hundred watts and be totally fine, that would be a very low amount of power. That's not the same when you put it into a pluggable. A pluggable, historically has been designed for 1 to 3 even watts, and even 5 watts in a QSFP. Like 5 watts in a QSFP 28 is still an extremely high power class that not every system will support. But in a lot of cases, these external transponders can be a little bit wasteful. So if all you're doing is taking this thing and if all you're doing with your transport platform is plugging it into your routers and you're the consumer bandwidth, if you're able to eliminate that, if you're able to take that transponder and put it inside of your device, you can save yourself a tremendous amount of overhead and cost and client optics and fiber and the the transmission systems themselves tend to be very expensive. So 400ZR was the attempt to bridge those two worlds. So what there's trade-offs, right? So on the coherent side, you have a greatly stripped down functionality. So 400ZR, the original 400ZR, only does 400 gig. It does it with a greatly reduced FEC. It has greatly reduced chromatic dispersion tolerance. It only works at a single like 69 gigabaud, 59 gigabaud rate. And on the pluggable side, you see push to be able to support much higher power ranges. So as you look at like QSFP DD, so the same QSFP plug but with a slightly longer connector on the back so it can be backwards compatible, they designed this thing to be 12 to 15 watts of power capable, which is a tremendous increase compared to the traditional designs, which are really focused on kind of 10 kilometer being the average power density seen in a pluggable. The other competing standard is OSFP, which is a much bigger, it gives you much more power. So you can do 15 to 20 watts of power in an OSFP. The trade-off being it's larger physical real estate and it's not backwards compatible with your QSFPs that make up your 100s and 40s and everything else. So I personally like QSFP DD better, but OSFP is out there. And the other thing is it makes a well-defined standard. So you can buy two different pluggables from two different vendors, and they're going to follow the same spec. So 400ZR was really built around this 80 to 120 kilometer reach. It's designed for 400 gig only. It's really, really designed for kind of campus metro, very simple stuff. It has a very reduced FEC, computationally reduced, so you can kind of get it down to 15 watts of power, and it's standardized by OIF. But then they said, all right, well, now that we've done that, can we make it a little bit more complex? Can we go back and add something more sophisticated? So then you have OpenZR Plus. So OpenZR Plus is designed to do much longer reaches. It's still not as good as an external transponder. I would say in today's technology, it's roughly about half as good. So if you wanted to use an external transponder instead of OpenZR Plus, you're going to double the distance that you're able to get out of that same bit rate by using an external transponder that is not power constrained. But in a lot of cases, ZR Plus can be very cost effective. If you're doing like a 500 kilometer shot or a 1,000 kilometer shot, it can still be fine. So it can work in different variations between 100 to 400. It has a more computationally complex OFEC, has a higher power requirement, so you're up to 20 watts, but that's starting to come down. And you're able to get that in, you're able to get ZR Plus and QSFP DD at this point. And it's defined by the OpenZR Plus MSA. So here's an example, here's a slide I gratuitously stole, kind of showing the different evolutions of coherent technology. So if you look at kind of the original like 2010 era, this was your 100 gig coherent, and it moved all the way up until to 200 gigs. So 2010 to 2015, you had that 100 to 200. It was very much based around 30 gigabaud. It was very much based around being able to fit inside a 50 gigahertz channel on a traditional system. Go away. And this was built on 65, 40 nanometer silicon processing. So your examples, your Acacia AC400 was kind of the Broadcom of the industry. It was a very common chip that's used by a lot of different vendors. You have folks like Infinera, Ciena, Nokia, each able to kind of create their own in-house DSPs. Then you move into the kind of 2017 to 2020 era. So this is your 400 to 600 gigabaud range, or 400 to 600 gig per lambda range. So you see that we're now up in the 60 gigabaud range. You're able to be much more intelligent. So your modulation isn't quite so, you have these different constellations that are a little hybrid. So they're not these perfect, I didn't even talk about constellations, but you have more advanced constellation designs in how you do your QAM. You have very real-time telemetry. It's much more sophisticated. So that's your Acacia AC1200, which is the thing that makes up a lot of third-party systems. And you also have like Ciena WaveLogic 4, or the Ciena WaveLogic AI is in this category, or there's a Nokia, there's the different ones. And then there's compact versions of it. So if you look at 400 ZR and ZR Plus, that's the compact. That's the how do we strip it down a little bit, still get these 400 gig rates, but make it very compact and power efficient. And moving into the modern systems, you're now into 90 and up to 120 gigabaud systems. So these now require kind of a flex grid system or very non-traditional ROADM or very non-traditional mux to fit these channels, but that's what you're doing to do these 800 gig and terabit level lambdas that are out there. So you've got everything from like the Sienna, the like WaveLogic 5e in the 90 gigabaud range, into now you're looking at like Acacia, Sim8, and stuff like that. That is in these terabit ranges. That's where we're at with kind of coherent technology. So now a little bit about engineering an optical network. So insertion loss. Even the best connectors and splices are not going to be perfect. So every time you put two fibers together in one form or another, you're going to get loss. So a budgetary figure that you use for planning is 0.5 dB, but the actual loss can depend greatly on, did you splice it? Is it connectorized and mated? Like, how clean is it? There's a lot of different factors that go into this, but we call insertion loss the penalty that you pay just for inserting the fiber. So you'll see that described as loss from the mux, loss from a splice, whatever it is. It's just the cost of doing business. So a really common example, if you look at a 40-channel DWDM system, 100 gigahertz space, you'll see like a 3.5 dB max loss for Mux Demux. When you look at an 80-channel system, you'll see that it's much higher. There's tremendous amounts more loss. Well, what's happening here is it's literally just two different muxes glued together with an interleaver. That's why you're seeing that much higher penalty. So that's why a lot of metro systems work on 100 gigahertz spacing. Is you're not amplifying, you're literally just going for a reduced channel count, greater channel spacing, but you're having much lower insertion loss. But you can also get insertion loss from mismatched core sizes, misaligned cores, air gap between fiber, not fully inserted, all kinds of ways. So when you talk about how do you run this on an optical budget, well, now you need to figure out like, well, how much budget do I have? So when you look at an optic and it says 10 kilometer, that is almost meaningless. That is very, very broad limitation. So you go, oh, I've got an 11 kilometer span, this won't work. That's not even remotely true. And really the problem here is that there are only certain categories. The only categories that exist from a standards point of view are 10 kilometer, 40 kilometer, 80 kilometer. In new 400 gig stuff, you've got 2 kilometer and 0.5 kilometer standardized sizes. But if you want to make a 20 kilometer optic, and most of the, if you look at a 10 gig optic today, you almost can't buy, it's physically impossible to go buy a 10 kilometer optic that will only do 10 kilometers. They're all designed to do 20 kilometers. There's no reason to make one that does less, because it's not any easier or cheaper to make. But because there is no standard for 10 kilometer, or 20 kilometer, we still call it 10, even though it's actually capable of doing much more. So what you really need to do is figure out, well, what's my transmit power? What's my minimum receive sensitivity? What are the impairments that I'm going to see? Like, what are the losses? What are the connector losses? And do I have enough margin for that to change over time? Another thing that's out there is the different ferrule types. So PC, which stands for physical contact, not polished connector, as many people think, is the standard blue connector. So what's happening here is it's got a very flat edge, and you put the two together, and that's how you get your mating. So the original PC was designed to have less than a minus 30 dB reflection. So this is, if you transmit signal this way, how much of it actually bounces back to you versus being sent. Modern things are all UPC. So that's the standard guaranteed down to minus 55 dB of back reflection. But the other thing you'll run into are APC, the green connectors. What happens here is you put a little bit of an angle on the end of the ferrule so that you'll get less back reflection. This is especially important for high power applications, and this is especially important when the fiber is disconnected. So if you have fiber that's plugged in and all of a sudden you unplug it, well, what's going to happen to that power? In a UPC system, a ton of it's going to be reflected back because it no longer has a mating to send its power to. In an APC system, what's going to happen is the power is going to be reflected back into the cladding, and it's not going to transmit back. So it can work with very high power systems without impact caused by reflections. we talk about the different 1R, 2R, 3Rs of regeneration. So 1R is like an optical amplification. It's literally just making the analog signal brighter, but you have no awareness of what's a pulse in any way, shape, or form. A 2R system is something that restores the original pulse's shape in some way, but it doesn't know anything about what the thing is. And then a 3R is the most amount of recovery that you can do, and that's one where you basically fully decode the signal and restore the original timing. You completely regenerate it, and this is what you're talking about when you go OEO, when you go optical, electrical, optical. That's a full regeneration, but it's effectively doubling the cost of the system because you've doubled the amount of transponders. Bit error rates, I'll skip for time. All right, tools of trade. So light meters. Simplest, easiest thing on the planet is something that literally just looks, it's called an OPM, optical power meter, or light meter. It just looks at the light and tells you how bright it is. A thing to remember is that it actually, the results that it shows you, you need to tell it what frequency of light you're expecting. So if you have it set on 1310 and you get a 1550 signal, that's going to be off by a few dB from what it actually is because you didn't set it right. But this is where you see people put it in the wrong mode and put it in dB mode and not dBm mode. So if you're ever trying to take a metered reading, if you're trying to look at something and see not what is the loss over the span from a known signal source, but what is the actual absolute power, make sure you're in dBm mode. Because if I had a nickel for every time an Equinix tech told me that they measured plus 70 on my fiber, which is not happening. An OTDR is a device that uses reflections to measure characteristics of the fiber. So you send out these very short pulses and you look at the reflections that come back and you're able to detect the different events. You're able to see where is it spliced, where is the fiber break, and you're able to tell distance from the endpoint. So here's an example of an OTDR output. So you see that it looks at a fiber span, it characterizes and it tells you, well, here's the event. So like 2.3 kilometers down the road, there's an event. 8 kilometers down the road, here's a splice and here's the reflections that come back. A weird one of this example, which I took from some random above net fiber from like 15 years ago, you see when it shoots up a little bit, that's what's called a grower. So that's what's happening when you have mismatched fiber types, that they haven't used the same type of fiber consistently through the thing. It creates these false spikes. All right, so common questions. Can I really blind myself by looking into the fiber? Otherwise known as big scary laser, do not look into beam with remaining eye. So laser safety is, there's 4 main classes that we talk about for safety. So class 1 is something that's completely harmless. So it's either completely harmless because the power is so low that there's nothing it can do to you, or it's harmless because you can't be exposed to it during operation. So for example, a DVD player is a class 1 because while the CD is in and the laser is on, the door is closed and you can't possibly see it. And class 1 is something that's only harmful if you look at it in a microscope. A class 2 system is something that's only harmful if you intentionally stare at it. So like you take your ordinary laser pointer, like, well, if I wanted to, I could take an ordinary laser pointer, stare at it, hold my eye open like this and hold it for a really long time. But you have to want to hurt yourself. Like if you, oh, there's a laser in my eye, I'm going to blink, I'm going to look away. So class 2 laser is something that falls into that category. A class 3 is something that you really don't want to have a direct exposure to because it can cause harm. So this can be if you've purchased a big internet laser pointer that looks like a giant, I call it the Department of Homeland Security back signal, the big beam that you can see into space that let's go aim it at a plane, what could go wrong? Those are very illegal. Those are class 3 lasers that can literally blind you. They can blind you with a reflection even. And then class 4 is something that like melts, burns, or destroys Alderon. It's something that you will know that it's there because it will actually burn you. So the different laser safety is highly dependent on the frequencies of light because the frequencies of light impact how it relates to human health. So there's 2 main classifications in infrared, which is where all the things that we talk about live in infrared. IRA is near infrared, so that's your 700 to 1400 nanometer, and IRB, anything from 1400 to 3000 nanometer, is your shortwave infrared. So IRB, you might think, well, 1550, that's a very high power, long haul transmission system. That's going to be more dangerous, right? Well, the human eye doesn't do a good job of letting this shortwave infrared through because we can't see it, so there's no point. So the cornea just blocks it out. It doesn't do anything to help us. So it's actually the infrared that is much closer to the light that we can see that is more impactful. So if you look at different power classes, the max power, if you wanted, for example, to be a class 1 laser, the max power that you can have in a system for IRB. So if you're at 1550 and you don't have some kind of safety auto shutdown feature that detects that there's a fiber break, the maximum power that you can transmit is plus 10 dBm. And if you go to plus 17 dBm, you're in a class 3R. If you go plus 27, you're in a class 3B, et cetera. But it very much depends on the frequencies. Routers, really, anything that you see come out of a router, anything that you see come out of a common pluggable is almost always going to be a class 1. Even your long reach, even if you buy an 80, 120, 200 kilometer optic, it doesn't transmit stronger. It receives weaker. So the thing that you actually need to care about in terms of like where might I see something that might be an optical safety issue is when you go through an optical amplifier. So if you go through a big EDFA that's putting out like a plus 23 or plus 27 dBm signal, obviously that can be very powerful. And those systems have to have auto break shutdown systems for safety. Raman amplifiers are almost always class 4. It's a tremendous amount of power that you pump back into the fiber to transfer power. And they, like I said, they all have the auto power reduction or shut off. But just simple DWDMs, just simple passives. So for example, you look at, an LR4 optic. An LR4 optic that transmits 0 dBm per lane times 4 lanes is a 6 dBm worth of power because of those 4 lanes. So the more, like a 1310, a very cheap, easy, or even an 850 nanometer, those are much more of an issue because of the amount of power of the multiple lanes than it is an 80 kilometer optic, which will probably transmit even, an 80 kilometer single lane optic would transmit less, but would have a higher receive sensitivity. So should I be wearing safety goggles in the colo? All of your client optics, almost always, except for rare exceptions, are class 1, so it's not even a thing. Even on an amplified system, the light really disperses rapidly as soon as it hits air. So you have to like stick your eye right up to it to have any kind of real, if you take the fiber and like, I wonder if there's anything in there. You have to do something like that for it to be a real impact. And like I said, all the high power systems are typically in IRB, so they're mostly blocked by the human eye. But don't be careful when you look at it through a fiber microscope, and don't like, let me just hold it up to you for a really long time and see what happens. But why would you even look in the fiber anyways, right? This is all infrared, like what's the point? Well, you can actually see the sidebands. So for example, if you look into an SR optic and you see red, even though 850 is outside of human vision, it's going to have a little bit of spillover. It's going to spill over down into the 750, and you're going to be able to see that. What you used to be able to do with digital cameras, so this is a cool trick with your phone, is you'd be able to use your phone and it would be able to see the infrared, but the modern, nicer phones tend to have a lot of IR filters on it for optical quality. But you used to be able to like see your remote controls work and stuff like that. So, can I overpower my transmit? Can I damage my optic with overpowered transmitters? Like I said, the way that they make a longer distance optic is to make it more sensitive in receive. They might make the optic transmit a little more, but you're generally talking about like a 3 dB difference. Like maybe we made it 3 dB hotter, but almost always all of your gain is in receive sensitivity. So there's 2 points that you care about. One is the saturation point. So it's the point at which the optic is blinded. It now takes errors and won't function correctly because it's too bright. And the other is the damage point. So where is this thing so bright that it now hurts the optic and won't be able to work even after you fix it? But really, the 40 kilometer optics are the ones that have the potential for, if you take a 40 kilometer optic and you plug them in right next to each other, it probably won't work. You're hitting the saturation point. If you take these 80 kilometer optics and you do that, or you do it without attenuation, you run the risk of damaging the optic. Graph that you can look at later. Do I really need to be concerned about bend radius? Yes. So especially on traditional fiber that's designed to be like outside plant in the ground, that's not designed to be bent, bend radius is a real issue. And in fact, when you bend the fiber too much, the light will literally just leak out the side. So there's systems called a red light that you just shoot a big bright red light down the fiber, and if there's a break, you'll just see the the thing glowing red where the break is. Modern bend-insensitive fiber is what you tend to find in every patch cable, so you don't have to worry about keeping these very precise bend radiuses. But you know, like a bend radius for a traditional, like a G652 fiber might be 30 millimeters. So you need to follow a very, very specific curve. Whereas modern G657 stuff, you can take it and wrap it around a pencil and you won't really have a problem. Can two different wavelengths talk to each other? Yes. Depends on the optic, but generally yes. So as a rule, your laser receivers, your photodiodes, will see pretty much anything between 1260 and 1620. So it might not see an 850 nanometer, but if you're a 1310 or a 1550, or if you're high in the C-band or you're low in the C-band, it really doesn't matter. The optic sees it all and it looks exactly the same in your classic client optics. The coherent receivers are the ones that lock onto a specific frequency, but your non-coherents, they literally just look at what's the total light coming in. So many DWDM systems are built around this premise. So you can have one wavelength going in one direction and a different wavelength going the other direction, and that's how you work over a single fiber strand. So you cut your total capacity in half because you require two channels to do bidirectional communication, but you're able to do that over a single fiber. The only gotcha to receiving something that's different from the power level that you expect is that your power meter might be slightly off. Do I really need to clean the fiber? Yes. So what many people don't realize is that there's a tremendous amount of mating force. So you have 45,000 pounds per square inch of pressure between these two glass surfaces coming together in a connector tip. So if you have a tiny piece of dirt in there, it can literally chip the glass. It can permanently damage the cable. So if you're in an environment where there's dirt, dust flying around after you pull a connection, you really want to make sure that you've got a cleaning kit, and those are super cheap, and you can order them anywhere on the internet. Other miscellaneous fiber information. How fast does fiber travel? How fast does light travel through fiber? So this is the math that you can use to figure out, does my trace route look right? Does my ping look right? So the speed of light, like I said, almost 300,000 kilometers per second. So if you look at SMF28, you can pull up the fiber specs and you can see that the core has a refractive index of 1.4679. So that is exactly 204,232 meters per second. So 204 kilometers per millisecond. Or if you do it in miles, that's about 126 miles per millisecond. Now, remember, you cut that in half when you look at ping and trace route, because what you're looking at is round trip time. So if you have 100 kilometers of fiber, 102 kilometers of fiber, you call it 100 kilometers of fiber, that's going to be responsible for 1 millisecond worth of latency, propagation delay latency from the length of the fiber itself in your ping or trace route. But why is the value much higher in real life? Well, fiber is rarely laid in a straight line. There's lots of rings, there's lots of slack spools, there's lots of dispersion compensation that might be out there, there's all kinds of other variants, and you're usually seeing some other effects in addition to just propagation delay. And that is it with exactly 0 seconds to spare.